The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays.
The mystery of high-energy cosmic rays. Presented by Science at NASA. Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere and high-energy cosmic rays from outer space. This daily shower, which never stops, is a sign of violent events in deep space. It's believed the majority of cosmic rays come from supernova explosions. When massive stars explode, they blast most of their material into space. The expanding shock waves can break apart interstellar atoms and accelerate the debris to unimaginably high energies. Other unknown cataclysmic phenomena may be at work too, especially for the most energetic cosmic rays. Eun-Suk Seo, a professor of physics at the University of Maryland, says, cosmic ray particles with energies as high as 10 to the 20th power electron volts have been measured on the ground. This is more energy than we have achieved in the most powerful man-made particle accelerators. But how do natural cosmic ray accelerators pump so much energy into these particles? This is one of the biggest mysteries in astrophysics. While indications of the energies of cosmic ray particles can be measured from the ground, Seo and colleagues have taken their study to higher elevations, directly measuring particles from space before they break up in Earth's atmosphere. The cosmic ray detector known as CREAM, the Cosmic Ray Energetics and Mass Investigation, has been launched to the stratosphere above Antarctica on board long-duration helium-filled balloons. By lofting the detector above 99% of the Earth's atmosphere, researchers get a better idea of what cosmic rays are like before they collide with nuclei in the air above the detector. CREAM is able to measure the energy and direction of each incoming cosmic ray particle and identify the particle type by measuring its charge, thereby providing clues to the particle's origin and acceleration mechanisms. Since 2004, the team has flown CREAM 7 times over Antarctica, accumulating more than 191 days of data from altitudes as high as 120,000 feet. They're about to go even higher. CREAM is heading for space. A reconfigured CREAM detector is scheduled to travel to the International Space Station in 2017 aboard SpaceX's Dragon spacecraft on a Falcon 9 rocket. Named ISS CREAM, it will remain installed on the Japanese experiment module, also known as Kibo, for at least 3 years. Seo says the ISS provides an excellent monitoring platform for high-energy cosmic rays. The station allows for long-term monitoring in lieu of multiple limited-duration balloon flights, providing direct, unimpeded access to incoming cosmic rays without atmospheric interference. The longer exposure times on the space station allow for the measurement of higher energies. ISS CREAM has a goal of measuring the highest energy possible for direct measurement of high-energy cosmic rays. She adds, the mysterious nature of cosmic rays serves as a reminder of just how little we know about our universe. For more high-energy science from beyond Earth's atmosphere, stay tuned to science.nasa.gov.
Dark Lightning, presented by Science at NASA. NASA's Fermi Gamma Ray Space Telescope was launched in 2008 on a mission to study high-energy phenomena in our universe. The telescope routinely detects things like flares, powered by black holes in distant galaxies, or outbursts from massive stars going supernova. So, in 2010, researchers were not surprised when the telescope was hit by a beam of high-energy positrons, the antimatter equivalent of electrons. That's the sort of thing Fermi is out there looking for. But they were surprised when they realized where the antimatter came from, not from some black hole light years across the galaxy, but rather from our own planet. The source was a thunderstorm just 3,000 miles away. Earth's magnetic field seems to have corralled about 100 trillion positrons from the storm into a tight beam and funneled them all the way to the spacecraft, explains lightning expert Joseph Dwyer of the Florida Institute of Technology. Something was producing antimatter above the clouds of Earth and hurling it into space at nearly the speed of light. But what? Dwyer and collaborators at the NASA Marshall Space Flight Center and the University of Alabama believe they have figured it out. The answer, says Dwyer, is dark lightning. Dark lightning may sound like an oxymoron, but there is growing evidence that it is real. Ordinary lightning happens when electric fields build up inside thunderclouds. Electrons rush from one part of the cloud to another to try to cancel out the growing voltage. The flash of light we see traces the path of the charged particles, which heat the air 5 times hotter than the sun. If Dwyer's ideas are correct, dark lightning is a competitor of ordinary lightning. It also tries to cancel out the thunderstorm's electric fields. The process, he says, goes something like this. Under the right conditions, electric fields in a thunderstorm can create a powerful avalanche of electrons, shooting upwards nearly as fast as light. The electrons collide with air molecules, in turn producing gamma rays. Earth-orbiting spacecraft have been observing gamma-ray flashes from thunderstorms since at least the mid-1990s. Next, the gamma-ray energy transforms into a pair of particles, an electron and a positron. Successive collisions between these particles and other air molecules create a new batch of positrons and electrons, and the cycle repeats. A continuous feedback loop forms, like nuclear fission. It's a natural, self-generated, self-sustained particle accelerator, says Dwyer. Once the feedback loop gets started, he says, it can discharge parts of a thundercloud as fast as lightning. And, because the cascading electrons and positrons generate more gamma rays than visible light, the whole process is practically invisible to the human eye. Researchers once thought that gamma-ray flashes from thunderstorms were a weird byproduct of ordinary lightning. Now they are thinking it is a sign of dark lightning instead. The gamma-ray burst monitor on board Fermi is excellent at catching these flashes. At the American Geophysical Union meeting last month, Valerie Connaughton of the University of Alabama in Huntsville explained how new data processing techniques have improved the burst monitor's performance even more. In mid-2010, we began testing a mode which allows us to locate many faint gamma-ray flashes we had been missing, she said. Now, team members estimate Fermi should be able to catch almost 1,000 flashes a year. With data like that, researchers hope to shed new light on dark lightning and solve its mysteries once and for all. For more news about dark and mysterious things in the skies of Earth, visit science.nasa.gov.
satellite, you're thinking something the size of a car or bigger. It's the size of a loaf of bread, and that's our satellite. There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding: TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength in evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.